Good afternoon, everyone. Thank you for showing up in Pittsburgh, and welcome to Geo-Structures 2024. I'm Jay McKelvey. I'm the conference chair. I've had quite the odyssey getting us here. This all started back in Charlotte at Geo-Congress 2022. I was attending a meeting for the technical committee, Earth Retaining Structures, and the chair at the time said, we need a geotechnical specialty publication. So having just gotten done my term as technical chair for GeoExtreme, I was like, run a conference. And that's a great idea. I was like, yeah, you can get them to write your proceedings, you know? And we don't have to spend a whole lot of work. Right. That's a great idea. Jay, can you take that on? And I had yes tattooed on my forehead. So why not have a specialty conference? So here we are, like 2.5 years later. We were able to convince the geosynthetics and underground construction technical committees to join in. And it's been quite the odyssey for us and quite satisfying. But here we are 2.5 years later. We have 34 exhibitors in the 2 exhibit halls. You won't even notice the difference between the 2. It's all right back behind me. We had 59 papers finally submitted. We have 7 keynote lectures for you, 4 panel sessions, and we have 2 session panels, which is kind of going to be more informal, and that will be happening concurrently with the technical sessions. Have to recognize our sponsors here. Keller and Nicholson did the platinum sponsorship. Schnabel did the silver. You can note the copper and the other corporate sponsors as well as the exhibits. So thank you all for contributing to our conference and making this happen. So here's the best part. So I get to introduce a good friend, which is awesome. Jorge Zornberg and I, we started our careers together. We met at a conference here down in Morgantown, West Virginia in '94. He was just finishing up his PhD at Berkeley, and I was presenting a paper on geosynthetics, and we both were at a conference that had nothing to do with geosynthetics, and we actually had lunch together with J.P. Giroux, and we were looking at each other like, why are we here at this conference? Because none of these people know what we're going to talk about. So it turns out about 1.5 years later, I joined him at Geosynthetic, and we worked together for 4 or 5 years before he decided to go off and become uber famous, which was really good. So he gave me all this great stuff to tell you. I have a couple things. It was like when we arrived at Geosynthetic, the principals thought like, oh, well, let's get these 2 young guys together, and their kids are the same age, right? So George had me over for dinner one night, and my oldest is a boy, his oldest is a girl, and at the time, boys were yucky and girls were yucky, so those 2 didn't get along at all. You know, it was kind of interesting. But nevertheless, we endured to have good friends. So let me give Jorge a proper introduction. Professor Zornberg has over 35 years of experience in practice and research in geotechnical and geosynthetics engineering. His research focuses on transportation, geotechnics, environmental geotechnics, geosynthetics, unsaturated soils, and expansive clays. He's from Texas, so those last 2, he has to do that. Otherwise, he has to move to another state. As an engineering consultant, he's been an expert witness in litigation, forensic geotechnical cases, and now here's the cool stuff, boys and girls. From 2010 to 24, Professor Zornberg served as president of the International Geosynthetic Society. That's the IGS, that's the acronym. He's authored over 500 technical publications, written several book chapters, and has been awarded 3 patents. Professor Zornberg has received numerous prestigious publications, including the Ralph Peck Award, the Cross Medal, the Collingwood Prize from ASCE, the Mercer Lecture from the International Soil Mechanics Society and the IGS, and the IGS Service Award. He also has the IGS Award and the Young Member Achievement Award. I have that one. He's also received the Presidential Early Career Award for Scientist and Engineer that he received from President George Bush at the White House. I mean, how cool is that? How'd you do that? In 2019, IGS established the Zornberg Lecture. Like I said, the man's become uber famous. Ladies and gentlemen, give it up for my dear friend, Jorge Zornberg.
Dear. All right. You can hear me. Very good. Excellent. Thank you, Jay, for this very personalized introduction. I'm so thankful to the organizing committee for having me here. It's a pleasure to be in Pittsburgh, close to Morgantown, where we met first. And the topic of my presentation is going to be, and it's coming, I think. There you go. Load-carrying geosynthetic-reinforced bridge abutments. This is a topic that is very dear to my heart. And essentially, you may know it with different names. You may come across them like true abutments. You may have seen it as GRS-IBS. And my objective here is to tell you that there are many of them that have been built. So if the Department of Transportation tells you, no, I don't want to be the first one building it, there are many that have been built. There are many advantages. And more than that, I'm going to show you those advantages in light of structures that have been pioneering in this technology. So not only there are many of them, but they have been built for quite some time. And I'm going to show you about the good performance that we have had in these structures for 30+ years. All right, but first, let me tell you, maybe there's one aspect that is complex, or more complex than what it should be, that is the terminology. So here you have a wall. This is a retaining wall. I'm going to call it here a geosynthetic reinforced wall. Sometimes we would call it an MSE wall, or if it is an MSE wall, mechanically stabilized earth wall, that has geosynthetic self-reinforcement, we can call it a GMSE wall. This is the wall. When you drive by Pittsburgh, you are going to see many of these walls in bridge abutments. Now, this is still a wall. It's a bridge abutment in the sense that it serves as an approach to a bridge, but it's still, we design it as a wall because the load from the girders, the load from the bridge is transferred more often than not directly to bedrock through deep foundations. So this is still a wall, but I'm going to call it here a geosynthetic reinforced bridge abutment. This is the most common, but this is not what we're going to be talking about today. We are going to be talking about this. So we're going to be talking about a structure in which the load of the bridge is transferred to the surface, to the top of the retaining wall. And this is what we're going to call here a load-carrying geosynthetic reinforced bridge abutment. Again, sometimes we're going to see it as a true abutment. Sometimes we're going to see it as a load-bearing GMAC bridge abutment. But this is, how do we design these structures? Because these are not longer just a retaining wall. This is also a reinforced foundation. So should we design them as a wall with a surcharge? And there are some of our design guidelines that essentially consider that. They design this structure as a wall with a surcharge. Or, which is both of them are geotech, but they come from different points of view. Or should we design it as a foundation? And as a foundation, we may consider it plate load testing, the bearing capacity versus displacement versus settlements. Or should we design it as a foundation without lateral support? And the truth is that both of them are correct, but both of them are going to be different points of view for the design of the same structure. Now, I am not going to be talking too much about design. Actually, in this conference, we're going to have Professor Ji Han talking about the difficult aspects of the design, or I could say, the technical aspects related to the design of these structures. Instead, my focusing here will be to focus on the benefits in the long-term performance, and what are the characteristics of these structures. Let me wrap up this issue about terminology. This is the world of GMSC walls, geosynthetic-reinforced walls. Within this world of GMSC walls, we have a fraction of them that are going to serve as bridge abutments. Only a fraction of these geosynthetic-reinforced bridge abutments are going to be load-carrying. The great majority of the ones that you're going to see are really abutments that really are designed as walls, and we're really only a fraction of them, and that's going to be the focus of this presentation, are going to be carrying the load of the actual bridge. Now, it may get a little bit more confusing. I'm not sure if you're familiar with the concepts of integral bridges. Integral bridges are bridges that do not have do not have joints, and the subsurface load transfer is integrated with a superstructure. Now, some of the load-carrying geosynthetic-reinforced bridge abutments are going to be integral as well. In the US, there has been a very productive, very important initiative that led to what we call the geosynthetic-reinforced soil integrated bridge system. Integrated is not integral, but many of them, and I'm going to walk you through what these are, and I'm going to consider them a subset of the load-carrying geosynthetic-reinforced bridge abutments. And so with this in mind, and I must tell you that not everyone agrees with this terminology. This is for internal consistency. This is what I am going to be using here today. But the focus is going to be on this green subset of load-carrying geosynthetic-reinforced bridge abutments. Okay, so in this presentation, I'm going to focus a lot on case histories. And the idea is that these case histories will document the benefits of choosing this type of structures versus more conventional structures, such as those that carry the load directly to deep foundations. And I'm going to highlight from those structures, I'm going to highlight those that have been pioneering, that early structures. Why? Because these are already 30+ years old. And if there were any questions about how these structures were going to perform, now we have a good information about this long-term performance. And let me give you some heads up. It's very good. And then I'm going to walk you through the characteristics of these structures. What are the type of geosynthetics that are being used? What are the type of facing? What is the type of polymers that are being used? And this is going to be based on a big survey that we have conducted about this type of structures worldwide. All right. So regarding benefits, let me tell you about, first I'm going to list those benefits, and then I'm going to walk you one by one in the form of case histories. So first, they are going to be, very often they are going to be selected because they minimize or eliminate the infamous bump at the end of the bridge. A very important reason. Another very important reason, reduced cost. Another, very important in some cases, they are going to be particularly suitable to maintain stringent deflection tolerances. And we're going to see something about their seismic performance. They are particularly flexible structures, and they're going to perform particularly well in under seismic loading. And finally, I'm going to show you some examples about complex constraints and the need to change unexpected field conditions. So all these will be while at the same time, I'm going to show you their improved long-term performance. So, and there are other benefits that I'm not going to focus on in this particular presentation. But again, I'm going to focus on this presentation, on these benefits. And for each one of them, I'm going to highlight their improved long-term performance. OK, so let me walk you through these case histories. And for that, I'm going to first take you to the Founders-Meadows log-carrying geosynthetic-reinforced bridge abutment in Castle Rock near Denver, Colorado. And in this particular case, this structure, which, by the way, is the cross-section that I just showed you, the main reason for selecting this particular structure was to minimize, or this was the main motivation by the designers, the Colorado Department of Transportation, was to minimize or hopefully eliminate the bump at the end of the bridge. It was constructed in 1998, so we have 25 plus years already of performance of this particular structure. This is how the structure looked like back in 1998. These are the two abutments, and this is soon after construction. And actually, it was the first of this structure, not the first in the US, but the first of this type that was constructed in a interstate highway. It was completed in less than a year in terms of construction. This was a 6-lane system and accommodated 6 traffic lanes and sidewalks as well. And it was heavily instrumented. Some could argue that because there were so many instruments, they added to the reinforcement of the structure. But these are some of the results that we found in evaluating the performance. What you see here are, in the vertical axis, the outward displacements, lateral displacements during construction of the structure. And in the horizontal axis, the vertical stresses as the load of this structure. And essentially, since this stage number 2 until stage number 6 is essentially the stages that correspond to adding the vertical load of the girders. And we're talking about vertical displacement of only lateral displacements of on the order of 6 millimeters. Quite very, very small lateral displacements during construction. But what was the real big question was, what about the time-dependent deformations after we opened this to construction? And here it is. So these are measured strains in the structure and different layers within the geosynthetic reinforcements. And we can see that there are some time-dependent deformations maybe after a year or so after construction, and pretty much those deflections after opening it to traffic stopped. What is more important is that the main objective of this type of this structure was, and this has been evaluated over the years, there has been, even after 25 years, no bump at the end of the bridge. Significant success of the main goal of this selection of this structure. And this is a year or so ago, the last inspection. And here we can see the view of this inspection of this structure, performing particularly well. A nice looking modular block type of facing and performing excellently over 25 plus years. So what is the significance of this first structure that I'm showing you, which is the Founders-Meadows log-carrying geosynthetic-reinforced bridge abutments? This constitutes the first type of this bridge constructed in a major highway. Monitoring results have shown particularly good performance overall, and specifically, there has been no signs on the development of the bump at the end of the bridge. All right, so this was one type of structure here in the US, and I'm going to show you structures all over the world, but let me start here with the US. But the second one that I'm going to show you is also the first of its kind, and is the Bowman Road a load-carrying geosynthetic-reinforced bridge abutment. This is in Ohio, in Defiance County, Ohio. This is a comparatively small structure because this was meant to be designed for low-volume roads and bridges on low-volume roads. And actually, this is how this structure looks like. Some of you may recognize this is a typical cross-section of what we now call the GRS-IBS type of structure. But the main motivation in this particular system was to reduce costs. So the county engineer was looking for alternatives to replace many of the bridges in the county and without the cost associated with that undertaking. And in working with the Federal Highway Administration, this ended up being the first of its kind, and it was constructed in 2005, shy of some 20 years ago. This is the typical cross-section of this GRS-IBS system. There are several components. This is a very, I could call it a very prescriptive system with very defined components, very specific materials, very specific geosynthetic types, some limitations in terms of the height and span length and other characteristics of the structure. And here we have the current site selection criterion. This is meant to be for bridge spans that are less than 140 feet, a wall height of less than 30 feet, comparatively low scour potential, unhandle that, and in principle, either competent or improved foundation soils. Now, the important aspect, and this comes directly from Warren Schlatter, the county engineer that originated this initiative in Defiance County. This was constructed led to a reduction of the span length rather than having the spill-through type of bridge. The fact that they ended up with vertical walls reduced the span length, and this led to significant cost benefits of this structure. Actually, it was so simple to construct that it was actually constructed using the county in-house labor and equipment. And here we have a view of the actual girders being placed in this particular structure, and led to a decrease in construction cost on the order of 21% in relation to conventional bridges, and opened in 47 days. Considering that this was the first one, Mr. Schlatter indicates that now they can build the same type of structure in perhaps half the time, based on the experience that they have gained over the years. And this is a view of the structure in 2005, August, some 20 years ago, right after construction. But this is 15 September 2024. Today's 17th, 2 days ago. This is how this structure looks like essentially right now. The structure has performed excellently over the years. And here we have a view of the facing, and the structure has been performing as intended for 20 years or so. And this was the beginning of a series of many. Actually, this preceded what eventually became one initiative from FHWA, which was the Everyday Counts initiative. And this was implemented in a series of additional structures all over the US. And here I'm just showing you some of the structures that followed this pioneer structure in Defiance County. When it comes to comparison of cost, this is coming from Daniel Alzamora. This is how they came up with this cost benefits of this structure in relation to in relation to conventional structures, some of it coming from the abutment itself, some of it coming from the fact that you're decreasing the span length in comparison to other alternatives. And but over the years, these benefits can be even significantly more improved because of the additional expertise that has been gained by refining the type of construction techniques and having crews that are more experienced with this particular system. And that's why in Defiance County, probably is the county today that has the more structures, the county with the most GRS-IBS in the nation. So here is Defiance County, the northeast of Ohio, and some 36 bridges as of 2018 have already been replaced using this technology. And it's not only in Defiance County, but Pennsylvania is one of the states that has benefited from this type of structure also the most. And here we have some 18 structures that have been built over the years in this particular, using this particular technology. So many different projects, and this was the beginning of a very successful initiative from the associated with the support of the Federal Highway Administration. So what is the significance of the Bowman Road load-carrying geosynthetic-reinforced bridge abutment? This project constitutes the first GRS-IBS. It validated the objective of its selection, which is a cost-effective solution. Monitoring results, this was monitored. Some other structures were more significantly monitored, and they confirmed the good performance of the system. And this actually became the precursor of what ended up being the Everyday Counts initiative. Okay, you may wonder what is so different between the two different structures that I showed you, and they are different. We design them differently. I'm not going to get into the details. I'm just going to tell you what the differences are in the design. And this is a little bit of a sidetrack because I'm going to show you a little bit about this, but even though my focus in this presentation are the case history. So what design methods do we have available in the US for load-carrying geosynthetic-reinforced bridge abutments? I would say, and many would argue, what are the main differences between one design method and the other? Many would argue that the main difference is, and I didn't tell you this, in the GRS-IBS, a very important characteristic is that the vertical spacing of the reinforcements is particularly small. According to the guidelines, need to be less than a foot. More typically, 8 inches. That's the vertical spacing of the structure. Some would argue that that's the main difference. That's not how I see it. The way that I see it is that the ASCE approach considers the design of a wall with a surcharge, and that's how we build the design method that follows into this. On the other hand, the GRS-IBS guidelines look at this from the perspective of a foundation. Foundation, what is a load settlement response of this type of structures? And I would argue that there is no right or wrong. Both of them have merits on the approach for designing it, either starting as a foundation and checking that the settlements are adequate, or starting the other way around. Starting as a wall and checking that the settlements are adequate, or starting as a foundation and making sure that the lateral supports and internal stability is adequate. Very recently, or reasonably recently, I'm going to call your attention to 2 references that attempt to reconcile these two, the potential differences between these 2 design guidelines. One is they are the results of an NCHRP project, and that essentially led to some recommendations for ASCE implementation on how to handle within the ASCE framework the cases in which you have comparatively small vertical spacing. If you Google it, you're going to pick it up very quickly. It's NCHRP 2441. Or alternatively, you can go to the very latest version, very recent version of GEC 011. that also incorporates some of this information. This is a 2023 reference, and if you type in Google HIF 24002, you're going to find it. You're going to find this very latest version, both of them telling you, or at least the outcome of some recommendations on how to handle, within the ASCE framework, how to handle comparatively small vertical spacings. But in a nutshell, essentially, the vertical spacing may affect some aspects of the determination of the maximum of the ultimate tensile strength that we adopt for design, and several other aspects. For example, for the maximum, the ultimate tensile strength in the convention, and by the way, ASCE nowadays has several different systems for you to design MSE walls. However, when it comes to load-carrying geosynthetic reinforced bridge abutments, I would say, and maybe G can correct me if I'm wrong, the only one that would technically apply is still the simplified method. And in this particular case, we do have the conventional way of defining the maximum tension in the different layers in the reinforcement. Essentially, what this this refinement, the proposed refinement, essentially indicates that we're going to go from this distribution to a uniform distribution with depth to define the maximum tension in the reinforcement, depending on whether the vertical spacing exceeds 16 inches or is below 18 inches, and somewhere in between if your vertical spacing is somewhere in between. The main aspect in this case is that in both cases, the tensile capacity, that is the summation of all the reinforcement forces, remains the same. All right, so this was the small sidetrack that I wanted to tell you about the design. But again, I'm back to my main route, which is not regarding design, but is about benefits. So we talked about two benefits. One is minimizing the bump at the end of the bridge. The second one was cost. Let me tell you about the third one, and I'm going to take you to Japan. Very different type of structure than the one that we designed here in the US. This is going to be in Nagoya, Japan. In Japan, the design of these structures, actually for railway systems, is particularly well established. I'm going to take you to the first of this type of structure, which is in the Tokaido Shinkansen rail line. This is the bullet rail line in Nagoya, Japan. And one of the main reasons for the selection of this type of system was the need for this high-speed railway to maintain very tight tolerances. This is 30 plus years, probably the oldest of these structures, what we're calling here in this presentation load-carrying geosynthetic reinforced bridge abutments. I have borrowed this following slide from Professor Tatsuoka that highlights the different potential concerns when designing a bridge abutment with conventional pile foundation. So we're going to have the lateral earth pressures acting, and these lateral earth pressures will lead to settlement, potentially down drag on the piles, potentially lateral flow on these piles, lateral displacements on the facing of the reinforced bridge abutment, and on the reinforced concrete abutment. And here we have the bearings. Unless this is a integral bridge, you're going to have the significant concern of maintenance with these bearings. And particularly when we have an earthquake, all these impact of settlements and lateral earth pressures and concerns with the maintenance of the bearings are exacerbated. So, but in this particular case, I'm going to walk you very quickly through how this structure is constructed. very differently than what we do. And the main difference is that they rely heavily on the rigidity of the facing. Most of our designs in the US, we have a facing and we need it, but typically we do not account for the contribution to stability of the facing system. That's not the case in Japan. So this structure, this is a geosynthetic, in this particular structure was a geogrid reinforced wall. And notice that is, in particular in the facing, there are some gabions. Actually, this was wrapped around geogrids that had particularly clean gravel at the facing. But notice that in this facing, we have some anchor elements. The reason that they have these anchor elements is that they are going to subsequently cast in place a rigid full height facing. These full height rigid facing will be integrated to the reinforced wall structure. So now when we load this system, part of the load is going to be taken by the rigidity of these rigid full height facing. So here we have the footings, and eventually we have the girders for the bridge, and this is typically for railway systems. So here we have the railway tracks. So this is how this particular system was typically constructed. And here it is. In 1992, this is the Nagoya load-carrying geosynthetic-reinforced bridge abutment right after constructed. And courtesy of Professor Tatsuoka, this is last year's view and inspection of the very same bridge, essentially 30 years down the road, and the structure has performed as intended for this long, extended period of time. So what is the significance of the Nagoya load-carrying structure? It successfully addressed the main objective of this system, which was to control the tight deflections that were needed for the railway system. It probably corresponds to the first of its kind. Some would argue that the concept of, I would still consider this a load-carrying geosynthetic-reinforced bridge abutment, even though some of the load is transferred to the foundation through the rigid facing. And the long-term performance has been outstanding. This was, what I just showed you was the first out of 3 generations of this type of system, but they have all been, the intention was to support the railway system, the high-speed railway system in Japan. Next, also, in terms of benefits, I'm now going to take you to Chile. And this is the San Francisco, not San Francisco, California, San Francisco in Chile, load-carrying geosynthetic-reinforced bridge abutment. In this particular case, this structure was constructed as an overpassing for a railway system and in the O'Higgins region in Chile. The main reason for this selection was to satisfy both static and seismic stability conditions. Long ago, 2001, 20 plus years ago. This is a view of the structure during construction. Even though this is in Chile, the method for construction and the characteristics are very consistent with what at the time was the ASCE design method. This is a view of the bridge, again, during construction. And this is right after construction of the structure in 2001. Something important happened in this particular structure. In 2010, 9 years after construction, Chile there were over 500 victims on significant tsunami. This was an 8.6 magnitude earthquake. And this is the epicenter of the system, and significant problems were in Santiago. And this is a view of the structure inspected right after the earthquake, 2010. And, oh, by the way, I didn't tell you, but this had a skew on the order of 35 degrees. And the great majority of the bridges that had a skew had failed in this particular earthquake. And here it is. Other than some cracks that were attributed to the significant skew of this bridge, this was a bridge that was just a load-carrying geosynthetic-reinforced bridge abutment. It was oriented east-west. And look at the construction. And I'm going to call your attention to these vertical steel bars. They are called, I don't know what they call it. They call them seismic bars. And my friends tell me that the rationale for these seismic bars is that essentially they are supposed to restrain some vertical component of the acceleration during the earthquake. But look at no impact on these seismic bars in this particular structure. But I'm going to take you to another structure, also oriented east-west, constructed the same year by the same contractor, 6 kilometers away, some 5 miles away from this structure, essentially subjected to pretty much the same peak ground acceleration. And look at it. This didn't have the skew that the previous structure did have, and there was a significant problem with the performance after the earthquake, which was very common in many other bridges affected between the epicenter and Santiago. And look at this. These are the seismic bars, and this is Las Mercedes overpass. And the seismic bars are clear evidence of the difference in performance between this one, a conventional reinforced concrete with piers structure. Compare these with the performance of the load-carrying geosynthetic-reinforced bridge abutment. Very significant difference in the performance, and perhaps one additional data point, but an important data point in the performance of these structures under seismic excitation. And a year ago, so here, other than some artwork in this particular structure, this is still performing excellently after some 20 years since its construction. All right, so the significance of the San Francisco load-carrying MSE bridge abutment, it was successfully demonstrated the suitability of this system for their performance, including seismic stability. This was tested and successfully passed the task that many other bridges did not pass after the 8.3 magnitude earthquake in Chile in 2010, and recent inspection after 20 plus years have shown the excellent long-term performance. One more case history, and I'm going to take you to Brazil. This is the Maringá load-carrying MSE bridge abutment. And in this structure is particularly, I'm going to take you to the state of Paraná in Brazil, Maringá city. And this structure was particularly relevant because of the very significant constraints, construction constraints. And in addition to that, it was constructed using backfill that would not meet the requirements of the backfill here in the US, comparatively fine-grained soil, when in 2007. This is a trench that had to be built. There was an undergrade railway, and the idea was to build a number of overpasses through this railway. And essentially what they did is they excavated first on one side, now they have constructed one side, But now on the other side as well, they were over-excavating the trench, building a reinforced salt structure, adding the vertical load on top of these bridges in order to create the overpass. Particularly significant, important constraints in the construction of the structure. This is such a big structure that it's perhaps hard to show you a good picture of this system. This is right after construction in 2007. And this is the performance after very recently, a year or so ago in 2023. Again, the characteristics of these structures, we have selected them because they all are early structures and they have all been recently inspected. And this is a view of the good performance of the structure as observed very recently. Significance of this system: the project was successfully constructed using locally available. These are residual soils, red clays as backfill material. Was constructed, actually, and this was an important aspect, the idea was to construct this structure without interrupting the railway system, so at no point during construction the railway system was interrupted. And it showed adequate performance, some shy of 20 years after construction. All right, so I showed you a number of reasons, and I talked to you about good reasons to choose this system: eliminating the bump at the end of the bridge, decreasing costs, good seismic performance, ability to accommodate important constraints, and all of them good long-term performance. But let me now walk you through where these structures are. And I'm going to take you on a tour, worldwide tour. And essentially, we've been working on identifying where these structures might be. Over 50 structures in the US, the Netherlands, and Japan. In the US, we have identified 220. My guess is that we are on the order, actually on the order of 300 of these structures in the US. Then we have in green the countries with between 11 and 50 of these load-carrying geosynthetic reinforced bridge abutments. Between 6 and 10, 2 and 5, and at least 1. So many of these structures have been, and this is particularly relevant worldwide in the sense that for countries where these systems had not been constructed, identifying that they have already been constructed and perhaps successfully performing is a good data point. So what I'm going to do now is I'm going to walk you through the characteristics, how similar or different these different structures are around the world. And I'm going to tell you about the span lengths, multiple or single span structures. By the way, the GRS-IBS structures are meant to be single span structures. Multiple types of facing, wide range of heights in the abutments, multiple types of geosynthetics with different polymers, and a wide range of tensile strength in there that leads to their design. And finally, a wide range of vertical spacing. Okay, and this is just to give you an overview of how wide the design, wide range of design of these structures we have had. When it comes to the span length, and this is the maximum span length in each one of the continents, this is associated per continent. The maximum span length has been in Asia. But if you actually get a cumulative distribution, kind of the 50th percentile is heavily influenced by the 200 20-plus structures in the US. So the span length is, in average, has been comparatively small, even though very significant span length have been constructed. In terms of the number of spans, also worldwide, we do have, even though in the US the great majority are single span structures, many structures worldwide have been with as many as 9 spans. So let me take you to the one structure that has 9 spans. This is in Australia. This is the Barney's Point load-carrying MSE bridge abutment. It is a massive structure. It's a massive structure in New South Wales. This is how the structure looks like. It has 4 terraces of reinforced soil, reinforced soil system with 4 terraces plus the beam. This is a view of the cross-section of the system. And this is the structure as right after construction. And it was constructed in 1993, so we're talking about a 30 years old system. Massive structure. The main reason for the selection of this system was potential problems associated with the settlements. So settlements were going to occur, but differential settlements was the main concern. And the structure has performed excellently since then. This is an inspection of the system last year. And as you can see, this massive structure has performed excellently over the 30-plus years. This is another view of the structure inspected last year. Now, when it comes to the facing type, the great majority, there is a significant number of structures that have been built using modular blocks. But there are other types of structures, particularly gabions as well. Now, this may be deceiving because when we see the different type of facing, even though there is a wide range of facing types, when we look at them per continent, the variety is not so significant. So for example, in the US or North America, heavily influenced by the GRS-IBS structure. So here we have a great majority of the structures being modular blocks, while the rest of the world, in Asia, the great majority being full height face reinforced concrete panels. And Europe, I would say a little bit of everything, but a fair amount of gabion type of facing. And this is a view of the first load-carrying geosynthetic reinforced bridge abutment in Germany, constructed using gabion facing. By the way, a water crossing structure. So yeah, there you go. Okay, so this was inspected 20 or so years after that, last year, and the performance of the system has remained as intended and without any particular problems. So when it comes to the heights of the different structures, there is quite a number. This is the maximum height in the different structures per continent. But if we look at the cumulative distribution, I would say heavily influenced by comparatively small height structures in the US. So this is the highest structure in South America. I'm showing you this one in particular because I think that it's relevant to see that even not necessarily in transportation systems, but also this is making its way into systems such as mining construction. This is the Yanacocha mine load-carrying geosynthetic reinforced bridge abutment. This is a cross-section of that particular structure. And when it comes to the different reinforcement types, I would say clearly geotextiles and geogrids have been heavily used, but the distribution is particularly affected depending on where you look at these structures. In the US, heavily influenced by the preponderance of GRS-IBS structures, the great majority being geotextiles. I could say in most of the rest of the world, the great majority being geogrids. When it comes to the polymer type, also these geosynthetics have been primarily polyester and polypropylene. And finally, let me take you through the structures they have been designed with a wide range, even though the selection of closely spaced vertical spacing leads to a comparatively small ultimate tensile strength requirement. Nonetheless, structures with significant ultimate tensile strength have been constructed. Here we have some in South America and in Europe in particular. This is the distribution of ultimate tensile strength in the different continents. And this is one example of that structure. This is the Maracajá structure in Brazil, designed using a comparatively high reinforced ultimate tensile strength, 400 kilonewtons per meter. This is comparatively high. And this is a structure designed with a facing of gabions and is recently constructed, but performing excellently since its construction. And finally, and I'm not going to show you a case history, but I showed you several of them with a different range of vertical spacing. As we discussed in the US, heavily influenced by the selection of closely spaced vertical spacing of the reinforcements, but that's not necessarily the case in the rest of the world. And this is the cumulative distribution of the structures that we have identified. All right, so my intention here was to walk you through why to choose these type of systems, what are the different benefits, and what are the different characteristics. Hopefully, I did convey to you that the concept of load-carrying MSC bridge abutments is not a new concept. And there are many good reasons to choose them. They have been demonstrated to be able to maintain, to eliminate or minimize the bump at the end of the bridge. They have been certainly successfully led to cost-effective structures. They have been able to maintain stringent deflection tolerances, excellent seismic performance, and being able to accommodate important constructability constraints. All of them in structures that have been performed between 20 or 30 years ago, and they have all been showing and performing as intended since then. In terms of the range of structures, I could say the US, Netherlands, and Japan for different reasons. I could say in the US, what governs? Low cost. In the Netherlands, what governs? Important considerations regarding settlements. In Japan, what governs? Important considerations regarding seismic performance. So good reasons for the countries that lead the number of structures in this selection of the system. Span lengths have been it has gone over a wide range of span lengths, in some cases exceeding 110 meters, and heights exceeding 30 meters. So some of these structures have been significant. Geogrids and woven geotextiles have been the geosynthetics of choice, particularly. And even though in the US we have designed the great majority with comparatively small or low ultimate tensile strength, important structures have been designed with comparatively high ultimate tensile strength. There are guidelines that require a comparatively small vertical spacing, even though structures with vertical spacing exceeding 1 meter have been designed successfully and have performed adequately. And wide range of facing selections have been characterized in this, the design of this type of structures. Okay, so after walking you through the benefits and the characteristics of this type of systems, this is a collection of information that has been gathered over a comparatively long period of time. Particularly, I would like to acknowledge the NSHRP, the contribution of my former student and now my colleague, Dr. Morsi, many contributors to the different case histories, including their recent visit and inspection of the comparatively old and early structures, and contributors to the survey, and my colleagues that have worked with me in this NCHRP project. And with that, I thank you so much for your attention.
Well, Jorge, thank you very much for this presentation. I think it was a beautiful exercise for a Sunday night after the Steelers game, right? You took us step by step in a very awesome process of how we have evolved, right? I think I speak for many of us here. We started our careers about 20 years ago. We started doing a lot of GRS design for the slopes, right? 1.5 foot spacing, the concept of the circle passing and kind of working as an anchor behind the, you pass the circle, whatever is behind the circle is your anchor and all that. Then around 2010, the GRS IBS starts, right? We also probably did a little bit of MSCs before. GRS IBS starts, and we go into the concept of now jumping from 1.5 feet to only 8 inches, as you explained it there. We're having more of a reinforced mass, right? Now it's not the concept of individual kind of anchor behavior, it's just a mass that we are creating. FHWA, Daniel Alzamora and Jennifer Nix and everyone involved, Mike Adams too, they put together this beautiful manual, and obviously the work that you did and many people in the room also did. And then now we go into these, GRS IBS limited by 30 feet, right? So here in Pennsylvania, we have been involved in many of the stars that you show, right? Very successful example. We also instrumented in Delaware, but we go to the point of the 30 feet, right? And then once we exceed the 30 feet, we cannot really use it. So in Pennsylvania, successfully, we have kind of going back into one of your first slides, when you show what you were not talking about, and I think it was the second, that we just go back and put piles. So we do a GRS, basically a GRS wall, and then we put piles, and we put the bridge on piles. It doesn't really take that many piles. It's similar in concept, even though it's completely different to an integral abutment, but it's just one row of piles, and we can support it like that, which is a great solution, but it completely kind of defeats the purpose of what you're Now, you successfully show us today, especially on the last few slides, that around the world, there is many examples, successful examples, exceeding 30 feet in height with absolutely no problem. So I guess my question after this long introduction is, what do you think we need to start implementing that, right? And we can go beyond the 30 feet and say, hey, this system applies for anything. You just need to adapt. One of my main concerns every time I see both the PennDOT and also the FHWA typical details is the seating of the beam, because the beam doesn't seem to go farther enough that you can have like a failure, like a little circle starting from there. So what are your recommendations if you can, just to move ahead from the 30 feet and start implementing in bigger scale?
Okay, thank you for the background and the question. So how to take in the US to structures that are taller, longer spans? I would say that the concept of GRS-IBS is an extremely successful initiative, but it has its objectives. Its objectives were mainly to allow a low-cost replacement of bridges in low-volume roads. Can that concept be extended? Now, because it relies heavily on experimental data and field data, and we cannot go too much, at least using those concepts, we cannot go without additional experimentation or additional analysis. We cannot go directly into different parameters. However, you can see that we can. So, and it turns out that the design of load-carrying geosynthetic-reinforced bridge abutments are honestly not that different than a critical. We have designed critical retaining walls. And this is one more, and I would consider it a bridge is a critical structure, and as such, it can be designed with proper considerations, design, starting from the GRS-IBS or starting from AASHTO. I think that I would claim that we can learn from both types of systems, but definitely I hope that the idea in here is that such designs are possible, and more than possible, they have been done, and that was the main message in here. These structures have been built 20 to 30 years ago. They have performed excellently, so now we know much better how to design 30 years down the road than what we knew at the time, so we definitely can do that. Thank you.
Sorry, too short. So, speaking of life expectancy, so when these structures were originally agreed to by the local, entities, what was that life expectancy? And then based on what you've shown us, has that life expectancy significantly extended?
I could say that the life expectancy, but I'm going to tell you my opinion, the answer is I do not know. What was as the designer's life expectancy. But I could say that it's no different than the 75 to 100 years of any other retaining structure. I think that early in the days, the big question was, are these structures, because you have a concentrated load, are these structures going to show time-dependent deformations? And that was the big question that we didn't know how to answer, and we needed data to prove, even though our calculations may tell us, no, you should not worry about time-dependent deformations, but it was good to see the data. And so because those time-dependent deformations did not materialize, I could say that even though you have a concentrated load, this is no different than any other critical retaining structures that we have designed. So I'm still going to stick to 75 to 100 years design life. Mm-hmm. Thank you for the question.
I have a question very much related to what Deborah asked. Many in the US, these are low volume roads. It's very unlikely that there's going to be a need to widen them because of functional obsolescence. But many of the international examples you show were carrying a lot of traffic. Have any of those structures to date required widening? And if and when you need to widen a GRS abutment, what might be the strategies?
To widen the structure?
If you need to widen the roadway, and thus you need to widen, it's a simple matter when you have a pile-supported bridge, although you do have to do something with the abutment. I'm asking, have you done it yet? And how are they going to do it? This is not going to be my problem. Maybe.
Yeah.
Maybe you have aspirations.
There's one. I'm just going to give you my thoughts. I would say that when you're going to go for reconstruction, you'd rather reconstruct a structure that has been constructed as a backfill and geosynthetics rather than reinforced concrete. So I didn't get into the information about carbon footprint. But if you start taking into consideration the input that we can get out of the end of the design life and how does overall the carbon footprint compare, these structures could compare so significantly better. Not only cost, not only performance, but also, I would say, sustainability. So I'm assuming that you're referring to reconstruction at the end of the design life. And I would say if you're going to deconstruct one of these structures, probably it's going to be much easier than deconstructing a reinforced concrete type of bridge abutment.
Reconstruction, absolutely. Widening while keeping the roadway in service is my question, and that seems challenging.
It is challenging. I can give you examples like the one that I showed you. It was a railway that essentially they had to maintain the railway operating all the time and in Brazil. And using this type of system was particularly, essentially the main reason, I don't know if you understood how it was. It was a below grade railway, and they had to essentially get the overpass. So rather than reinforcing the sides of the trench, and in order to do that, I don't know, solenoid walls, they would have needed to stop or interrupt the railway. So essentially they excavated the trench wider and they built the reinforced structures, and on top of that they created the overpass. So I'm not saying that this is the only approach, but this ended up being a approach that facilitated a reasonably difficult construction constraints and real estate for this particular structure. I'm not giving you a straight answer, but I think that these are thoughts. I think that is also valuable. I think that there are positive experiences that point towards the question that you're asking. Thank you.
So wonderful case history. So we, 30 years of experience. We're basically at the engineering half-life, right? Mm-hmm. Being a geosynthetic guy, right? Now, we know when we go with the simplified approach, we've got a lot of strength in our back pocket to start with, right? You know, we're seeing a fraction of the strains that we would estimate, right? Should we begin a program to start thinking about how these things are going to behave in 40 years when they start experiencing creep rupture? I mean, we're talking about the nature of that is catastrophic. There won't be prolonged deformation in advance of that.
My take, and this is my take, creep rupture is a myth, in my opinion. We are defining reduction factors in order to be reasonably away from creep rupture. However, when we do all these calculations for creep rupture, we test the geosynthetics in isolation, and they are not in isolation. They are under the confinement of soils, so they may have deformations, but in order for you to have those time-dependent deformations, there needs to be deformations of the system. Mm-hmm. So even though it's, I believe, and the other important aspect is that if you creep a geosynthetic and you're almost at the verge of creep rupture, but you stop the loading and now you do a rapid loading, pretty much you still have almost the ultimate tensile strength of the material. So I don't think that we're going to start seeing structures in 100 years failing because of creep. They may fail, and they may achieve their serviceability design life. I don't think that the failure type that we're going to see is going to be due to creep rupture.
Thank you.
Thank you, Jay.
Got one more. Given the failure rate of MSE structures in North America is reported pretty high, 8 to 10%, what can we all in the room learn from some of both the project delivery and qualifications that might be included in specifications internationally and QA/QC processes that are in those specifications for some of these more major structures shown in your presentation? I think we saw a lot of examples in North America that are those low volume roads that you referenced, but some really impressive structures internationally. And so do you see any major differences to those project delivery and QA/QCs in the specifications?
The great majority of the structures that have failed have one out of two. Mainly have something to do with water, and mainly has something to do with potentially having a backfill that has not been the one that we have envisioned to begin with. I'm a strong believer that we can design for comparatively fine-grained soils, but we need to design for them. And maybe having a great drainage system is not enough. We may need to start designing the structures, assuming that the drainage fails. And in those cases, I'm pretty sure that most of the structures that we have seen failing, had we considered what-if scenarios that considered water, the presence of water, we would have seen that those structures would not sustain. So I would say that is, yes, quality control specifications. And if you relax those specifications, and again, I'm of the opinion that we can't relax them, we need to design appropriately for them. Thank you. Very good. Thank you so much.